Welcome to Advanced Java Programming at Portland State University. In this screencast, we continue our discussion of the core Java APIs that are included in the Java programming platform. We'll be focusing on classes in the java.util package, which provide a number of useful and handy classes, or general purpose utilities for working with Java programs. We're going to see some of the original utility classes, things like string tokenizer, vector, hash table, and stack. Then we'll focus some attention on the collections classes, an API of Java classes, interfaces, and exceptions that allow you to group objects together in very useful ways. Then we'll take a look at how to work with dates and times in Java using the standard date, calendar, and locale classes. And we'll also discuss system properties and a couple other things along the way also. Okay, JavaUtil string tokenizer is a class that's used to parse a string, to take a string and break it down into its constituent parts. String tokenizer is a kind of an old school way of doing things. There's also regular expression support that was added in JDK 1.4. While I won't cover it here in this discussion, I encourage you to go look at the API documentation for java.util.regex, that package, which has a number of facilities for providing Perl-like regular expressions. So the string tokenizer has a constructor that takes a string to be parsed and another string whose characters delimit tokens. And tokens are just parts of a string. Think about breaking a sentence down into words. Each word is a token, and the characters that delimit tokens in a sentence are things like space and period and comma. Punctuation like that. By default, if you don't specify a set of characters that delimit tokens, it'll use white space. So once you have one of these string tokenizer objects, you can ask it things like, how many tokens are there remaining to be consumed? Give me the next token, and are there any more tokens to be returned by the string tokenizer? Okay, let's take a look at an example of string tokenizer. So here's a simple main method that takes two command line arguments. The first one is a string to be parsed, and the second one is the delimiters that will be used to parse the string. We create a new string tokenizer, and then we'll iterate over that string tokenizer while it has more tokens to return. And then we'll simply ask for the next token and print it out. So when we run this program with arguments like this comma is comma a colon sentence period, with delimiters of comma and colon, we'll see that there are four tokens. There's this is a sentence, right? We told it that the comma and the colon were delimiters, and so it finds four tokens. This is a sentence. Okay. And you can imagine how you might use a string tokenizer in some of your projects for advanced Java programming, parsing dates and date times and things like that. Now on to the collection classes. Now, the first release of Java had several classes that were all about collecting objects together. Classes like vector, which provide a growable, ordered collection of objects, basically an array that could get bigger and smaller. There was a subclass of vector called stack, which gave you all the behavior that you had with vector, but also push-pop semantics. And then there was also hash table, which mapped a key object to a value object. And at the time, these were really great. It was so nice to have a language in which you didn't have to write your own hash table, your own growable array. And so people found these to be really useful, and I think really having these collection classes were so useful that they really introduced a lot of people to object-oriented programming, to being able to have a reusable API. People really like this stuff. However, they tended to be kind of bulky and slow. They were they were designed at the same time the language was. There were some things that the API authors didn't realize about the internal implementation. And so to augment this collection API and also provide some better implementation, there was a new API in a follow-on release introduced called the Collections API. So fundamentally, the Collections API starts with a bunch of interfaces that are in the java.util package. So there is an interface called collection. A collection is a very abstract notion of, well, a bunch of objects all together. And then there are sub-interfaces of collection like list, set, and sorted set. There's also a small hierarchy of what are called iterators. Iterators is an object that lets you, well, iterate over a collection. And so there's iterator and something called list iterator. And there's also a couple of interfaces, map and sorted map. Now, map provides you the same kind of operations as a hash table does. Maps a key object to a value object. And there is a subset of map, there's a sub-interface of map called sorted map, which gives you sorted keys in your map. And we're going to spend a little bit of time talking about these interfaces and what kind of behavior they give you. So first off, there's Java util collection. It's this very abstract concept of just some object that groups other objects together. And it has behavior like add. You can add an object to a collection. You can ask whether or not that object contains a given object. You can ask if it's empty. You can also get its size. Then you can get one of those iterators, and we'll see an example of an iterator later, but the whole idea is that an iterator is an object that iterates over one of these collections. That lets you very easily just visit every object in that collection. And you can remove from a collection. So here again, this collection is this very abstract concept. List gets a little bit more specific. Now lists are collections that are indexable, meaning that there's the concept of an element at index 0, 1, 2, 3, 4, 5, however big your collection is. And so the list interface has all of the methods of collection and then adds a couple more. So for instance, there is an overloaded add method introduced by list, which will add an object at a given index. And you can also get and set an object at a given index. So give me element 4. Set the value of element 5 to this other object. And lists also allow you to get a list iterator in addition to the regular iterator. And we'll see in a little bit that what a list iterator does is allow you to iterate both forwards and backwards over a list. Because collection does not define the order in which the objects are stored, are related, you can only iterate one way over the collection, and really then it's not iterating in order. It's just here are all of the objects in the collection. Java util set is a type of collection in which the elements of the collection, elements of the set, are unordered, and each element in the set is unique. Now, the way it determines whether or not so when you go to add a new element to a collection, since all of the elements in the set are unique, it will use the implementation of the add method will use the equals method of the object being added to determine whether or not it is already in the collection. And so here's an example of how the collections API leverages the fact that every object in Java has an equals method, right? The set needs to determine whether or not an object is already in the collection. What does it do? Well, it just uses the equals method that every object has to determine whether or not that element already exists in that collection. It's also interesting to note that set does not add any new behavior to the collection interface. Unlike list, it doesn't add additional methods. It doesn't overload methods to take additional parameters. But what it does is it adds more semantics to the class. So here again, it provides the same behavior, it provides the same contract, let's say that, but it provides different behavior by implementing the methods differently. So for instance, in just any old collection, it doesn't say whether or not, so in a capital C collection, there is no guarantee about the ordering of the objects. There's no guarantee about the uniqueness of the objects. What sub-interfaces like list and set do is add more semantics, add more information to the collection. Okay, finally, there is a sub-interface of set called sorted set, whose elements are not only unordered and unique. They are not only unique, but they are ordered. So the whole idea is that you've got the set semantics in that they're unique, and sorted set says, well, not only are they unique, they are also ordered. So sorted set has a notion of the first element in the sorted set and the last element in the sorted set. And in a little bit, we'll see how exactly those elements are ordered. Okay, I've mentioned these things called iterators a couple times, and here are the details. So an iterator is this interface that only has a couple of methods, and what they do is provide the ability to iterate over the objects in some collection. So you have a collection, and you want to, like capital C collection, and you'll note that there's no get method. Actually, same thing with a set. You can't say, get me element number 5 because the objects inside a capital C collection or a set are not ordered. There's no concept of the fifth element. Instead, what you do is you get an iterator, and you get an iterator over that collection, and you ask it, hey, are there any more elements to return? By invoking the hasNext method, and then once you determine that there are, you can invoke next and then iterate over the contents of that collection. The iterator interface also has a remove method, which will remove the the current element that you're looking at, or that the iterator is visiting. It will remove that object from the underlying collection. This is a good thing to do because by removing it from the iterator, it keeps the by removing an element from the underlying collection via the iterator, it keeps the iterator up to date with the contents of that collection. However, it's not guaranteed to be implemented. There might be some data structures for which remove is a very difficult or expensive operation to implement, and so it's not guarenteed to be not guaranteed to be implemented by every collection that you can iterate over. There's an iterator, which just goes in one direction, just says hasNext. There's a sub-interface of iterator called listIterator that allows you to iterate in both directions. And in addition to being able to remove an element from the underlying collection, you can also insert an element into the underlying list by invoking the add method. So it has add, has previous, and you can also get the index that would be returned by next or previous. I've got to admit, listIterator is kind of neat, and I understand how it fits into the pattern. I can't say that I've used it very often. Normally, if I wanted to do this kind of manipulation on a list, adding things or figuring out which index I'm looking at, I would just just call it on the list directly and not bother with the list iterator. Anyway, okay, a couple more interfaces to look at. JavaUtil map. So a map will map some key object to some value object. And it's like a hash table that we learned about in our data structures course, right? So the whole idea is you got methods like put, which will create one of these mappings from one object to another. Now, think back to your data structures course. How do maps work? Well, they can be implemented using something like buckets and a collision list, right? And so what do you need to do that? Well, you need to have an equals method to determine whether or not the key matches the given key in the collision chain. And then you also need to have a hash code to figure out which bucket it goes in the first place. And this is where the hash code method that every object implements is used. So the fact that object has an equals and a hash code method allows the collections to have any old type of object as their keys, any old type of object as a key in a map in this particular example. And this is good because otherwise what you'd have to do is, have some interface that you implement that says, oh, I've got a hash code and blah, 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 blah. Well, the designers of the Java API decided they didn't want to have to, they wanted to let any object be a key in a hash table. And so every object in Java has an equals and a hash code method. So you put into a map to create a mapping from one object to another. And then when you want to get the value for a given key object, you use the get method. And you can also ask the map whether or not it contains a given key, contains a given value. And when you want to iterate over the contents of a map, you've got a couple of options. So there is the key set method, which returns the keys in a map as a set. Now, why are the keys in a map a set? Right, there's just a bunch of objects. Shouldn't that be a collection? Well, if you think about it, by definition, the keys in a map, each key object should only appear once, right? Because if I put object A to object B, and then I put object A to object C, that mapping between A and B has gone away and replaced with A to C. But that A, so therefore, the A object is unique. So since the keys in a map are unique, when you ask for, hey, give me all of the keys, that will return you a set. And so here again, the Java API uses its interface that represents a set of objects, a collection of objects in which each object is unique, as a set. So key set returns a set. Values, which returns all of the values in a map, however, returns a collection. Now, why does it return a collection and not a set? Well, there's no guarantee about the uniqueness of the values in a map, right? The same value object could be associated with multiple different keys. So since there's no guarantee about the uniqueness of values, values returns a collection. So you can get key set to get all of the keys. You can get values to get all of the values. There's also a method called entry set, which returns an object that gives you, the key value pairs. That is a set because each one of those is going to be unique because all the keys are unique. But it's an easy object that allows you to both get at the key and the value associated with that key, all in one fell swoop. Okay, those are a bunch of interfaces. Now, interfaces are all well and good, right? You should be programming to the interface. You should familiarize yourself with these interfaces. However, at the end of the day, you need to be able to instantiate some object that implements that interface. So what the JDK provides, first of all, is this layer of abstract implementations that provide a lot of common and shared behavior for the eventual concrete classes. So things like, hey, there is a collection interface. We're going to have an abstract implementation of that collection interface that provides a lot of the functionality, which is then shared among multiple subclasses, but it doesn't provide all of it. We'll delegate the most specific functionality off to the concrete classes like hash set or linked list or array list. So what are some of those concrete implementations? Well, there is so the implementations of Java util lists are things like array list, which is a list that's backed by an array, and linked list, which is a list that's backed by a linked list and also provides stack-like behavior. So it's got some methods that aren't on list. And finally, the vector interface was retrofitted to implement, the vector class was retrofitted to implement the list interface. Now, the list interface is the same across all of these implementations, right? It doesn't, it can't change across them. So why do we have 3 different implementations of the list interface? Okay, well, we just talked about vector already, and okay, that was sort of grandfathered in. It was retrofitted to implement the list interface, so it still does what it's always done. It just does it with a slightly different. It supports a different contract. But why do we have both an array list and a linked list? Well, as I'm sure you learned in your data structures course, a list that is backed by an array has different performance characteristics than a linked list, and they each have their own pluses and minuses. Right. So on the one hand, storing elements in a growable array, an array list, it is more compact to store. There are fewer objects involved, and you can also read from it, do get operations very, very quickly. But adding to an array list, growing an array list can be expensive, right? It reaches a certain threshold, or maybe it fills up all the way, and now you've got to grow your array, which means creating a larger array underneath it, doing a copy from the old array to the new array, et cetera, et cetera. And so if you're going to have a lot of insertion operations on a list, an array list might not be the best choice. In terms of performance, linked list is kind of the opposite. In a linked list, every time that you add to a linked list, you got to create another node, you got to find the right place to put it, and so that means that inserting and random access can be slow compared to an array list. However, if you are always adding to the end, let's say you've got a queue or something like that, or if you're always removing from a linked list, that the operation can be much faster on a linked list than it can an array list. So, but the nice thing about this is that if you program to the interface, if all you do is deal with, in the vast majority of your code, just deal with the abstract list interface, your code doesn't care whether or not it's working with an array list or a linked list. Okay, there are a couple of implementations of maps. There's there's hash map, which gives you a constant time get input access. And then there's tree map, which sorts the keys and gives you presumably faster log and get input. Although your value of n has to be pretty big before it really makes a significant difference performance-wise. A couple other interesting implementations of map. There's something called identity hash map, which implements the map interface, but changes the semantics slightly in that instead of using dot equals to compare the key values, the keys to determine whether or not a key is already present in the map, it uses identity comparison, the equals equals operator instead. And then there's linked hash map, which keeps track of the insertion order and allows you to do things like find the mapping that the key value pair which has been in the map the longest. And this allows you to very easily implement things like least recently used algorithms for data that you're keeping around. Finally, there are a couple of implementations of sets, hash set and tree set. This is a set that's backed by a plain old hash table. Basically, it leverages the fact that keys in a hash table or a hash map are unique to then implement a set functionality. And then tree set, which implements the sorted set interface and is backed by a data structure called a red-black tree. And you can Wikipedia that to learn more about it. Okay, let's see some of these classes in action. So here is a program that creates a couple of collection instances and then prints them out. Let's start with our main method, and then we'll take a look at the print method second. So what do? We create a new array list, and we assign it to this variable C of type collection, which, let's see here, why is that legal? That's legal because an array list implements the list interface and list interface subclasses from the collection interface, so a list is a collection, therefore an array list is a collection. Okay, that's cool. Okay, and all I'm doing is adding a bunch of stuff to this collection, so I don't really care that I'm underneath the covers I'm using an array list. I can just treat it as a collection and just call add 3 times on it with the strings 1, 2, 3, and I'll print it out. Now let's look at this print method. Okay, so print takes a collection, so some collection of objects, and it's just going to, well, iterate over it and print it out. Now remember, the capital C collection interface has no notion of the order in which the objects appear. So it just knows that, well, there are a bunch of objects here, and I will let you iterate over them. There is no concept of saying, give me the first one, give me the second one, give me the third one. Collections just don't have that. Instead, they have this iterator object that then lets you visit each one of them. So you get an iterator, and they're going to loop. While there are more objects to be gotten from the iterator, give me that object and print it out. That simple. Okay, back to our main method. So we printed out our array list, which was stored in collection C here. Print an empty line. Now I'm going to create a hash set, which is the implementation of that set interface, with the contents, the initial contents of the hash set will be that collection C. So there are various constructors to hash set, and one of them takes another collection to use as an initial seed population, if you will. I'm going to treat that hash set as a set. Actually, I could just create it as a collection. I could just treat it as a collection too, because all I'm going to do is add to it. And I'll add 2 more elements, 4 and the string 2, and I'll print that out. And again, because a set is a collection, I can pass it to the print method with no problem, because the print method will take any collection. The fact that you're giving a set, that's great. The compiler will allow that, but the print method itself will just treat it as a collection. So what do you get when you run this program? Well, first of all, you get the output of the contents of this first collection is printed 1, 2, 3, and then the contents of that second collection is printed, which is 1, 3, 4, 2. So this is kind of interesting. The first thing that I notice here is that while the array list maintains the order in which you added elements, the hash set does not. Right? I added it 1, 2, 3, 4, and instead I get 1, 3, 4, 2. Now note, I called the add method 5 times. But at the end of the day, there's only 4 elements in the hash set. Well, why is that? Well, because when I added the string 2 for the second time, the hash set that guarantees that all of its elements are unique determined that the string 2 already was contained in the hash set and didn't add it a second time. So as a result, there are only 4 elements in the collection, even though I've called add 5 times. So there's there's lessons about what the concrete classes do, but there's a bigger lesson in this, which is don't worry about the details. Program to the interface. So for instance, that print method, all it took was a collection. It didn't care that at runtime you gave it an array list or you gave it a hash set or whatever. It just said, hey, just give me some collection. That's all I want to know about it, because all I need to do about it is get its iterator and walk the iterator. And this is something that I'm going to mention again and again in advanced Java programming. This program to the interface. Worry about the abstraction, don't worry about the concrete, because that gives you a lot of flexibility, right? So we saw that print method now can handle any type of collection that's thrown at it. And also, by working more abstractly, it allows you to change out the underlying implementation without having to worry about the code that is using that implementation. Now, if you look at the APIs for the collection classes, you'll notice that they take objects. So the add method takes an object, and iterators return objects. But what if you want to have a collection that has primitive types? Things like ints, doubles, and booleans. Those aren't objects. How do you put them into a collection? Well, this is one of the things that the wrapper classes can be used for, right? We learned about those in a couple of screencasts ago. The whole idea is that you've got an object that represents a primitive type. So if you want to put primitive data into a collection, you can do something like the following. Create your array list, has a collection, and just add, instead of just the int4, add a new integer object, or a new double object, or a new boolean object, and go ahead and print that out. Now, that's kind of a pain in the butt, right? You've got to do a whole bunch of extra typing. Creating those objects seems really kind of inefficient and things like that. So Java 5 introduced a new language feature called Autoboxing, which automatically converts primitive data types to their wrapper objects and vice versa. And Autoboxing is applied just about any place an assignment takes place. So when you assign a value to a variable or a field, when you call a method call, when you cast, this autoboxing takes place. So here, if you look at this code as an example, you see here we can now call integer.value of a string. Even though value of returns a capital I integer, autoboxing will automatically convert it to a little I int here, and we don't need to do anything special. Similarly, now we can add that int I to a list, and then when we get it out, we can cast that list. The get method returns something of type object. Now we can cast that object to a capital I integer, and it'll automatically get converted into a little I int. So autoboxing is a very useful feature of the language because it allows you to treat primitives as if they were objects. But as we saw, the content of a collection is still capital O object. And so it meant that when you worked with them, you had to do a lot of casting, right? Like we saw in this example. Even though we put an integer, into that list, when we got it out, well, we didn't know that it was an integer, so we had to cast it. So we had to tell the compiler, hey, listen, you think that there is a capital O object, is any old object in here? I know that it's a big I integer, and so I'll cast it for you. Another language feature that they introduced in Java 5 was something called generic types, which, among other things, allowed you to specify the type of objects that a collection may contain. So, for instance, now just having a list, you would say list less than string greater than, bracket string greater than, and you pronounce this as it's a list of strings. Similarly, you can have a list of longs, and notice that not only the list has a generic type, but also the implementation of that list. In this case, array list has a generic type. So now I have an array list of longs, which is a list of longs. And what this gave you is now compile time type safety of your collections. So for instance, if I have a list of longs and I attempt to add a string to it, the compiler will tell me that I've done the wrong thing. So now you can find out at compile time that there's a problem with your program, that you're trying to add a string, instead of finding out at runtime. And depending on how good your unit tests are and how good the data that you test with is, you might not find out about the problem for, well, hours, days, weeks, or months. So by strongly typing your collections, by leveraging generic types, your code is more readable and you feel more confident about it. While overall, generic types help the language a lot and help the Java developers a lot, it did add some complexity to the type system. It's important to note that even though a string is an object, an array list of strings is not a list of objects. An array list is a list, but in this case, an array list of strings is not an array list of objects. Consider this example. So let's say I have a list of strings, initialized as a new array list of strings. Okay, so far so good. If I was able to assign that list of strings to a list of objects, and now I just have a list of objects, the compiler would not be able to detect that this line is invalid. Right? If I say list of objects.add new integer, well, that's okay as far as the compiler is concerned, because all it knows is that a list of objects contains, or LO contains a list of objects. Integer is an object, I should be able to add it. But it's not. It was created as an array list of string. So what the compiler does is that it will complain if you attempt to make an assignment like assigning a list of strings to a list of objects. Now, another thing that generics did is that it forced you to type a lot more. Now, modern IDEs, and you can check out how IntelliJ does it, will hide a lot of the verbiage, the boilerplate associated with using generics, but it's still there in the language. So if you're looking at the source code, you can still have really ugly expressions, really ugly assignments like this. Okay, I have a list of map of string to string. That's an array list of map of string to string. You see how I had to separate it over two lines? It gets really big. Well, Java 7 introduced what's called the generics diamond that will ask the compiler to infer the generic types on the left side of the assignment. The generic types are actually inferred on the right side of the assignment. It allows you something like this. Here I have a variable called data, which is a list of map of string to string, just like up above. But now all I have to do is say, hey, new array list diamond. And the compiler will then infer that, oh yeah, this array list right here is an array list of map of string to string. It is a nice time saver and allows you to do things like, hey, if you need to change what data is, you need to change what the contents of that list is, you can do it just on the left side of the assignment. You don't need to worry about what happens over on the right. Okay, I want to say a few more words about iterating. So what happens when you've got a collection that is modified while it's being iterated over? So you have a collection, you've got an iterator over it, and what happens if somebody else modifies the underlying collection? So let's look at a little program that does it. Okay, here I have a list of strings that contains 1 and 2. I'm going to get an iterator over that list. Note here that the iterator for a list of strings returns an iterator of strings. I'm going to iterate over that iterator. And then I'm going to get in the next element from that iterator. And here again, because iterator is strongly typed as an iterator of strings, the next method of that iterator doesn't return just any old object, it returns a string. So no casting here. I'm going to say, okay, well, if that string that I'm iterating equals 1, I'm going to modify the underlying list. I'm going to set the element at index 0 to be start. And if I run this program, what do I get? Well, I get something called a Java util concurrent modification exception. So most iterators in Java are said to be fail fast, meaning that they have the smarts to detect when the underlying collection is modified. For instance, its size changes or something like that. And when it does detect that the underlying collection has been modified, the next time you call the next method, it will throw a concurrent modification exception. This is good, right? Maybe you have 2 threads of execution, or maybe you don't realize that some operation you're doing while you're iterating over the collection modifies the underlying collection. And this is probably not what you had in mind. The iterator could get out of date. Some iterators take essentially a snapshot of the collection when they're created, and then they iterate over that snapshot. If the underlying collection is changed, is that snapshot still valid? That's sort of dependent on what you're using the collection for and the nature of the modification and things like that. So the iterator isn't going to try to be too smart, because that smarts is hard to document and communicate. Instead, it's just going to throw up its arms and say, "Oh, wait a second! The underlying collection was modified. I'm going to blow up with a concurrent modification exception." In the scenario in which you honestly do want to modify the underlying collection, you should modify the underlying collection via the remove or add, if it's a listed iterator, a method of the iterator itself. By calling remove on the iterator, if it's implemented, it will remove the object pointed to referred to by next, or that would be returned by next, from the iterator and also the underlying collection, and that will keep all of the bookkeeping up to date. So here again, if your iterator got a snapshot at a certain point of time, it'll update the snapshot, and then it'll update the underlying collection. And the nice thing about this is that it immediately will tell you that something is wrong, that something is out of date, instead of allowing you to continue on your merry way and most likely have some unexpected and maybe non-deterministic behavior. That being said, the concurrent modification exception is an exceptional state, and while many collections support it, will have our fail-face, not every collection is. And so then you can't always rely on it. So for instance, if you have a list and you simply replace an item, the iterator may not fail. Now, it might execute correctly, or it might simply miss it. So you shouldn't rely on the fail-fast behavior to as sort of the proper logic of your program. The concurrent modification exception should only be relied on to make you aware of a bug. So we've seen this pattern where you get an iterator and then you have a little while loop. You say, hey, while the iterator has next, give me the next one and then do something with it. In Java 5, they introduced this new enhanced for loop syntax. I think we talked about it when we talked about arrays, but they're also applicable to collections. So here, if I've got some collection, I can say, for each object in collection, print it out. And if you have a collection of strings, you can say, for each string, s, collection, print out that string. And this syntax is really well. It's nice. It works really well. It's nice and compact. But note that you don't have a reference to the iterator object that is used to iterate over that collection. And 95, 98% of the time, that's perfectly okay not having that iterator. If you really want to have the iterator, well, just use the old syntax where you have the collection and you get its iterator, and then you iterate over that. Okay, we've seen some examples of working with collections like lists. Let's take a look at the map real quick. Here I have an example, much like that program that printed out the contents of a collection. Now I have a program that prints out the contents of a map. I'll start with the main method. We create a new hash map. Notice we're using the diamond operator so that it'll all fit on the slide. And I'm going to map a string to an animal. Animals are a bunch of classes from the object-oriented programming discussion. The keys of the map are going to be the names of the animals, and then the value is the animal object itself. So I'm going to add a new human named Old MacDonald, a new cow named Bossy, a new sheep named Clyde, and a new duck named Louise. I'm going to print it out. So this is a hash map that I'm passing to the print method, but the print method doesn't care. It's going to take some map that maps strings to animals. And what is it going to do? It's going to get all of the keys in the map and print out the key and the value. The way it does is that it uses that enhanced for loop to say, hey, for each string key in the key set, so that's the set of all the keys in that map, give me that key, give me the value for that key, and notice because this map is strongly typed, I don't need to do any casting of the animal or the string, and I'll print out the key value pair. Sure enough, when you run this program, you get, Clyde says ba, Bossy says moo, Old MacDonald says hello, and Louise says quack. It's important to note that with the hash map, the order in which the elements were added, Old MacDonald, Bossy, Clyde, Louise, has nothing to do with the order in which they come out. Right? The hash map just implements the map interface and doesn't make any guarantees about the order in which the key value pairs are stored in the map. And the iterator doesn't make any guarantees about the order in which they're visited. So it's completely up to them. I guess the important thing to understand is that you don't care about the order. Of course, there is some order, there has to be, but you don't care about it, and therefore your program shouldn't rely on it. You just want to be able to get all the keys in the collection. You don't care what order they come in. Again, maps use the hashcode method of the key object to determine which bucket to either put the key value pair in, or when you're looking for the value based on a key, to look up the key. And as you are iterating down the collision chain in the bucket, the key object is compared to each key in the key value pairs in the collision chain using the equals method. So again, the equals and the hashcode method that are implemented by every Java object are used with the collection classes. So what does this mean? Well, if you implement your own classes that you want to be used as keys in a map, it means that you should override equals and hashcode. And you should make sure that your equals and hashcode method have the appropriate semantics so they can be effectively used as keys in a map. So for instance, any two objects that are equal must have the same hashcode. And there are some very nice recipes, if you will, to follow for implementing your equals and hashcode method. I won't get into them here, but if I ever do a bonus lecture, the Java tips and tricks, we talk about some details there. So there are some collection types, like sorted set and sorted map, that will compare various objects and will order them. And so the whole idea is that this object comes before another object. Think about Java-lang integer, right? Integers have an ordering. The integer for 1 comes before the integer for 5. Same thing for characters or strings. Classes that implement the Java-lang comparable interface are said to have a natural ordering, meaning that they know how to order. That an instance of this class knows how to order itself relative to another instance. So, for instance, strings, integers, doubles, dates, all that kind of stuff implement the comparable interface. Therefore, they have a compare to method that compares itself, x, to another object, y, and returns an int value with the following semantics. So, if I come before this other object, the compare to method will return a negative integer. If I am the same, I should return 0. And notice that the compare to should have the same semantics as the equals method, right? So if two objects have a compare2 of 0, they should also be equal to each other. And if I come after, if I am greater than the other object, the compare2 method should return a positive int. Now, the comparable interface was augmented with a generic type that specifies the class of the object that it can compare itself to. Most often, you will compare, yourself to another instance of that same class. Although it's possible to be a little bit more fancy than that. That's probably beyond the scope of this discussion right now. So you have these comparable objects, and unless you tell it otherwise, the classes and methods that sort objects, things like sorted sets and sorted map, will respect the natural ordering. So if I say, hey, give me a sorted set of strings, it will call the compare2 method to sort those strings. To demonstrate natural ordering, I've built a little class called cereal. It models a breakfast cereal. A cereal has two fields, a name and a price, and it implements the comparable instance. That's comparable to cereal, meaning that it knows how to compare itself against another cereal instance. So its compare2 method compares, well, this cereal to another cereal instance, C2. And we'll say that two cereals, that cereals are naturally ordered based on their name. And so the compare2 method simply says, well, I'm going to delegate the responsibility for comparing two cereals off to, well, their names. So it compares two cereals by saying, well, this .get name, how does it compare to the other guy's name? This is a pretty common technique that you will delegate, that will use the fields of the object to determine how two objects compare. Now, because I have overridden compare2 or implemented compare2 based on the name, I also need to override equals to compare, compare to determine whether or not this object is equal to another object, again, based on its name. So, now, unlike compare2, there is no generic type for equals, so it's still object. So, first I say, well, if that object is another cereal, then I'll compare it using its name. Otherwise, they're not obviously not equal. So, I get another cereal object, and I say, well, how is my name, this .get name, the same as the other guy's name? If they are, then the two cereals should be considered equal. And because I override equals, I also have to override hash code. I have to override it so that two cereals that are equal have the same hash code. And the easiest way to do that is just to delegate the hash code behavior off to the name also. And so obviously, if there are two cereals that have the same name, they're going to have the same hash code. Okay, so here's an example of actually creating some cereal instances and adding them to a sorted set. I'm going to have a sorted set of cereal, which is a new tree set. I could have used the diamond operator here, but I didn't. And remember, tree set is a concrete class that implements the sorted set interface. I'm going to add three cereals to that sorted set. I'm going to add some total for $3.56, some Raisin Bran, and some Sugar Crisps. And then I'm going to iterate over that sorted set of cereals, and print each one of them out. And so when I run it, sure enough, they are printed in alphabetical order: Raisin Bran, Sugar Crisps, and total. So what the tree set did is that it respected that natural ordering. When I added each one of these cereals, the tree set said, aha, this is an object that implements the comparable interface. It's going to use that. It's going to use the compare2 method of the comparable interface to determine the order in which the cereals should be stored. What natural ordering does is it allows the author of the class to specify how instances of the class are compared. And that makes a lot of sense, right? You've got something like, strings. They know how to order themselves. You wouldn't want to have to force the person that's using the string, the set of strings, to have to do the sorting for you. That being said, there are some times in which you're going to want to have a custom ordering. So not the natural ordering. You're going to want to impose some ordering over the collections and over the elements in the collection. And for that, there is an interface called comparator. So a comparator is an object that implements an algorithm, a sorting algorithm, to sort objects using criteria other than the ones used for their natural ordering. A comparator is said to specify a total ordering over a set of objects. So a comparator has a compare method that takes two objects and returns an int, and that uses the same contract as the compare2 method, right? So if object 1 is less than object 2, it returns negative. If object 1 is equal to object 2, then it returns 0. If object 1 is greater than object 2, it returns a positive int. And again, comparator has a generic type that specifies the type of object that you're comparing. The sorted collections like tree sets and tree maps have constructors that will that are overloaded to take comparators. So you can pass a comparator in when you're creating your new tree set or whatever. And here's an example of one of those comparators that imposes an absolute order over objects. So let's say instead of sorting cereals based on their name, I want to sort them based on their price. So here is a comparator that sorts based on price. I have a class called cereal comparator, which implements comparator of cereal. Now, because it's cereal, the compare method takes two cereals. I'll get the price of the first, the price of the second, and then I will basically say, hey, the price of the first one is greater than the price of the second, return 1. If it's less than, return -1. If they're the same, return 0. And here's a main method that uses that comparator. I'm going to create I want to have a set of cereals. Actually, it's a sorted set, but it's also a set, which is a new tree set of cereal, and it's going to sort its elements using a new cereal comparator. Now I'm going to add 4 cereals. I'm going to add Cap'n Crunch for 259, Trix for 329, Count Chocula for 259, and Fruit Loops for 245. And I'm going to iterate over my set and print each one of them out. And when I run it, sure enough, I see that the cheapest cereal, Fruit Loops, is printed first, then for 259, Cap'n Crunch, and then Trix. Now, why wasn't Count Chocula printed out? I added 4 cereals, but only 3 came out. Is there a bug someplace? Did I get something wrong? Well, no, not really. If you go back to our comparator, all we compare on is price. And we added 2 cereals with the same price, Cap'n Crunch and Count Chocula. So when I added Count Chocula, the tree set used the compare method, and the compare method said, well, wait a second, I already have a cereal in here whose price is $2.59. I don't need to add another one because it's already there. Forget it. And that's what happens here. So think about some ways in which we could change our comparator to maybe be a little bit better behaved, or provide more ordering based on more attributes than just the name. Okay, I won't spend too much time on this, but there is a helper class called JavaUtil Collections that has all sorts of static methods that can come in handy when working with collections. So for instance, there is a method called max, which will return the largest element in a collection using the natural ordering. There's also one that will take a comparator and use that for comparing. If I want to have a list that contains n copies of a given object, you can use n copies. If I want to have a list that just contains, a set that just contains one object, I can do that with a singleton method. Similarly, I can sort a list using some comparator, and I can create an unmodifiable map or an unmodifiable set over another map or set or collection of data. And this can be useful when maybe you want to return a copy of an internal data structure, but you want to make sure that it's not modified. Any attempt to modify one of these unmodifiable maps will result in an unsupported operation exception being thrown. There's also another helper class called JavaUtil Arrays that give you all sorts of helper functions for dealing with arrays. So you want to take an array and turn it into a list, you can use asList. If you want to perform a binary search or determine whether or not 2 arrays are equal, you can do that too. If you want to populate an entire array with a given value, you can do that with the fill method, and you can also sort an array in place. The examples I list here are all ints but they are overloaded to operate on any different kind of object, all kinds of arrays, doubles, objects, etc., etc. Okay, I think it's a pretty good discussion of the collection classes. But before we go, I want to actually dig into the API documentation so that and explain a couple things to you so that you know what you're looking at when you look at the API docs. Okay, let's look at the classes in Java util. Okay, let's look at something like list. Okay, so it's saying it's an interface list of type E. Now E is the type parameter, is the type variable that represents, well, the type of elements in the list. And so now let's look at some of the methods, like add. So when I add something to a list of E, I add an E. And when I get something out of a list at a given index, I get an E. And when I get an iterator over a list of E, I get an iterator of E. So let's look at iterator. Iterator has a type variable E. And it has methods like next that return an E. So these used to be, before Java 5, these used to all be object. But now they are of type E. Similarly, if you look at map, map has two type parameters, k, which is the type of the keys, and v, which is the type of the values. And its put method puts a key k to some value of type v, and will return, I think, whatever used to be associated with that k key, which is of type v. Interestingly enough, for backwards compatibility, the remove method of from a map still takes an object and will return a v. So I think what it allows you to do is have a map of, let's say, strings to animals, and you can call remove capital I integer, some integer object from it. It doesn't hurt. It's going to return, it's not going to have any effect because an integer can never go into that map. But the API, the API still allows you to make that call. And again, here the values method returns a collection of v, and the key set returns a set of k. This entry set method is a little interesting. Entry set returns a set of the key value pairs. And what the strong type of this is that it's a set of a class called map.entry of k to v's. And when we see inner classes, you'll understand more about what map.entry is all about. But let's just leave it as it's a little tuple class that contains a key and a value. And the key is of type k, and the value is of type v. Anyway, I just wanted to leave you with that. So the collection classes are very useful. I think you'll be finding them of great help with your assignments, and they also give you experiences working with generic types. Okay, well, that's all for now. As always, thanks for watching Advanced Java Programming at Portland State University.